Hi students, today we are going to start our next chapter after nuclear structure, and that is nuclear transformations. In nuclear transformations, we deal with the different types of nuclear reactions in which the nucleus emits a number of particles so that it changes from one kind of nucleus to another. Now, radioactivity is the example of a nuclear transformation where a heavy, unstable nucleus emits radiations and gains stability. The phenomenon of radioactivity was discovered by Antoine Becquerel in 1896. It is defined as the spontaneous disintegration of a heavy, unstable nucleus by emitting highly penetrating radiations. And there are three types of radiations which can be emitted: alpha, beta, and gamma rays. Now, the three important features of radioactivity are: first one, when an unstable nucleus undergoes alpha or beta decay, its atomic number changes and it becomes a nucleus of a different element. നിങ്ങൾക്കറിയാം ഒരു ന്യൂക്ലിയസിൽ നിന്ന് ആൽഫ അല്ലെങ്കിൽ ബീറ്റ പാർട്ടിക്കിൾ പുറത്തു വന്നാൽ അതിൻ്റെ ആറ്റമിക് നമ്പറിൽ വ്യത്യാസം വരുന്നു. അതുകൊണ്ട് തന്നെ ഇത് മറ്റൊരു എലിമെന്റിന്റെ ന്യൂക്ലിയസ് ആയി മാറുന്നു. ഇത് റേഡിയോ ആക്ടിവിറ്റിയുടെ ഒരു പ്രധാന ഫീച്ചറാണ്. അതായത് റേഡിയോ ആക്ടിവിറ്റി സംഭവിച്ചു കഴിഞ്ഞാൽ ഒരു എലിമെന്റിന്റെ ന്യൂക്ലിയസ് മറ്റൊരു എലിമെന്റിന്റെ ന്യൂക്ലിയസ് ആയി മാറുന്നു. The second feature of radioactivity is that the energy liberated during radioactive decay comes from within the individual nuclei without any external excitation. നമ്മൾ പുറത്തുനിന്ന് ഒരു എനർജിയും കൊടുക്കാതെയാണ് ഈ റേഡിയോആക്റ്റീവ് ഡീകേ സംഭവിക്കുന്നത്. അതിൻ്റെ ഉള്ളിലുള്ള എനർജി ഉപയോഗിച്ചിട്ടാണ് ഈ എനർജി ലിബറേഷൻ റേഡിയോആക്റ്റീവ് ഡീക്കേയിൽ നടക്കുന്നത്. The energy liberated during radioactive decay comes from within the nuclei without any kind of external excitation. That is the second feature. Third feature, radioactive decay is a statistical process that obeys the law of chance. അതായത് ഒരു സാമ്പിൾ തന്നാൽ, ഒരുപാട് റേഡിയോആക്റ്റീവ് ന്യൂക്ലിയൈ ഉള്ള ഒരു സാമ്പിൾ തന്നാൽ ഇതിൽ ഏത് ന്യൂക്ലിയൈ എപ്പോൾ ഡീകേ ഏത് ന്യൂക്ലിയൈന് എപ്പോൾ ഡീകേ സംഭവിക്കുമെന്ന് നമുക്ക് പ്രെഡിക്റ്റ് ചെയ്യാൻ പറ്റില്ല. നമുക്ക് ഒരു പ്രോബബിലിറ്റി പെർ യൂണിറ്റ് ടൈം പറയാനേ പറ്റുള്ളൂ. അല്ലാതെ കൃത്യമായിട്ട് അവിടെ ഇന്ന കാരണം കൊണ്ട് ഇന്ന ന്യൂക്ലിയൈ ഡീകേ ചെയ്യും, ബിക്കോസ് ഓഫ് ദിസ് റീസൺ ഓർ ദിസ് കോസ് ദിസ് ന്യൂക്ലിയൈ വിൽ ഡീകേ. യു കനോട്ട് jot out a relationship like that in radioactive decay. It is simply a statistical process which obeys the law of chance. So we can only ascertain a particular probability per unit time for radioactive decay. So these are the three features of radioactive decay. The first one is when an unstable nuclei undergoes radioactive decay, it becomes a different nuclei of a different element. Then the energy liberated during radioactive decay comes from within the individual nuclei, and radioactive decay is a statistical process. Now, the three types of radiations emitted, I've already told. Those are alpha rays, beta rays, and gamma rays. Alpha rays are helium nuclei, beta rays are beam of electrons, gamma rays are high energy photons. Now, the radioactivity of an element arises from the radioactivity of one or more of its isotopes. So, potassium has a few stable and some radioactive isotopes, a few stable forms and a few radioactive isotopes, and these radioactive isotopes are responsible for radioactivity. Uranium has only radioactive isotopes. Now we deal with a new term called activity. What is meant by activity? The activity of a sample of any radioactive nuclide is the nuclide is the rate at which the nuclei of its constituent atoms decay. It gives you the rate of decay of its constituent nuclei. So the activity of a sample of any radioactive nuclide is the rate at which the nuclei of its constituent atoms decay. If capital N is the number of nuclei present in the sample at a certain time, then its activity is given as capital R is equal to minus dN by dt, where N is the number of nuclei present. Okay, so the activity is given by R equal to the rate at which the nuclei of the constituent atoms decay. So the rate of decay is given by dN by dt. Now that is activity. Now what does this minus sign indicate? The minus sign is used to make activity a positive quantity, as dN by dt is intrinsically negative. Okay, because the activity goes on decreasing with time. More and more of the atoms will undergo radioactive decay, and dN by dt is a decreasing quantity which is intrinsically negative. So to make it positive, we put a negative sign. Now, the SI unit of activity is becquerel. 1 becquerel is 1 decay per second. The commonly used units of activity are 1 megabecquerel, which is 10 raised to 6 becquerel, 1 gigabecquerel, which is 10 raised to 9 becquerel, and so on, are the appropriate units of activity. SI unit is becquerel. So, we defined what is activity, we wrote down its equation, and we wrote down its SI unit. Now, the traditional unit of activity is curie. It is defined as the activity of 1 gram of radium, radium 88 to 26. 1 curie is equal to 3.7 into 10 raised to 10 decays per second, which is 37 gigabecquerel, because 1 becquerel is 1 decay per second. So this is the relation between curie and becquerel. Now the other units which are commonly used, 1 microcurie like 10 raised to minus 6 curie, etc. So all these things, I think it's familiar to all of you. You have already learned all these things in your lower classes, but it's very important for our exams now too. Now examples of activity. A luminous watch dial contains several microcurie of radium. Ordinary potassium has an activity of 1 millicurie per kilogram, as it contains small proportion of its radioisotope potassium 1940, etc. Now we come to radiation hazards. Radiations from radionuclides ionize the matter through which they pass. So radiation from these radioactive nuclei will always ionize the matter through which they pass. And all ionizing radiations are harmful to human tissue, and prolonged exposure can cause permanent damages. And the consequence of these exposures include cancer, leukemia, changes in the DNA of reproductive cells, resulting in physical deformities and mental handicaps, etc. So that much about radiation hazard. Now, a very important thing, very important topic, how do you measure the amount of radiation or the radiation dosage? How can you understand this much amount of radiation is safe for us, this much is above that limit is dangerous, etc. can be understood from the radiation dosage. It is measured in units of sieverts. Okay, so 1 sievert is defined as the amount of radiation that has the same biological effect as that produced when 1 kilogram of our body tissue absorbs 1 joule of X-rays or gamma rays. അതായത് നമ്മുടെ ബോഡി ടിഷ്യൂ 1 കിലോഗ്രാം ബോഡി ടിഷ്യൂ 1 ജൂൾ ഓഫ് എക്സ്റേ അല്ലെങ്കിൽ ഗാമ റേ അബ്സോർബ് ചെയ്യുമ്പോൾ എന്ത് ബയോളജിക്കൽ ഇഫക്റ്റ് ആണോ അവിടെ ഉണ്ടാവുന്നത് അതേ ഇഫക്റ്റ് പ്രൊഡ്യൂസ് ചെയ്യാൻ വേണ്ട റേഡിയേഷന്റെ അളവിനെ നമ്മൾ 1 സിവാട്ട് എന്ന് വിളിക്കുന്നു. അതായത് 1 കിലോഗ്രാം ബോഡി ടിഷ്യൂവിൽ ശരീര ടിഷ്യൂവിൽ 1 ജൂൾ എക്സ്റേ അബ്സോർബ് ചെയ്യപ്പെട്ടാൽ എന്തൊക്കെ ബയോളജിക്കൽ മാറ്റങ്ങൾ അല്ലെങ്കിൽ ഇഫക്റ്റ് ആണോ അവിടെ ഉണ്ടാവുന്നത് അതേ ഇഫക്റ്റ് പ്രൊഡ്യൂസ് ചെയ്യാൻ എത്ര അളവ് റേഡിയേഷൻ വേണം എങ്കിൽ ആ അളവിനെയാണ് നമ്മൾ ഒരു സിവേർട്ട് എന്ന് പറയുന്നത്. That radiation amount or radiation dosage is called 1 sievert. Now, common unit is millisieverts. Okay, so that is the definition of uh, the unit of radiation dosage, that is sievert. Next, we come to the sources of radioactivity. Uh, all radioactive elements like radon, uranium, thorium, all are sources of radioactivity. Now, natural source of radioactivity are the cosmic rays coming from outer space, and some rocks and soils on the surface of the soil present on the surface of the earth. Then some radionuclides are inherently present inside our body too. Okay. Now, examples of a useful process involving ionizing radiation and radioactive nuclides, X-rays, gamma rays are all used for medicine and industrial purposes. Then radioactive sources are used in nuclear reactors to produce energy, etc. Next, we come to some technical terms that you use in our study in nuclear transformations. One is half-life. The time variation of the activity of a radionuclide is shown here. Activity, I told you, it decreases with time, because as the number of atoms that undergo decay, the number of atoms that undergo decay will increase with time. So the activity of a given sample will decrease with time. And as per activity law, capital R is equal to R0 e raised to minus lambda t, where R0 is the initial activity, R is the activity at any given time t, and lambda is the decay probability, that is probability of decay per unit time. Now, half-life is defined as the time taken for the activity to drop to half of its initial activity. That is, when R0 drops to half of R0, that time required for R0 to drop to half of R0 is called the half-life of that particular radionuclide. Now, we are going to find out the equation for half-life. I've already told you the radioactive activity law is given by R is equal to R0 raised to minus lambda t. When t becomes t half, R must be equal to half of R0. So when you substitute it here, take log on both sides and then simplify, then you get t half is equal to 2.303 log 2 to the base 10 by lambda. That is, t half is equal to 0.693 by lambda. So this is the equation for half-life. So larger the decay constant, greater is the probability of the nucleus to decay in a certain period of time. That is, larger the half-life, larger the decay constant, smaller the half-life. So greater is the probability for the nucleus to decay in a given period of time. So I hope half-life is clear to all of you. Next, we come to the radioactive decay law. If a sample contains capital N undecayed nuclei, and Dn is the number of nuclei in the sample in the time dt, then Dn is equal to minus of N into lambda into dt. Okay, so where N is the number of particles present in the sample, and lambda is the probability of decay per unit time, and dt is the total time, so that you get the amount of nuclei present in the sample at that instant of time. Now, dn by n is equal to minus lambda t, integrating on both sides, integrating dn by n from n0, the initial number of nuclei in the sample, to the number present, capital N, n0 to n, dn by n is equal to integral 0 to t minus lambda dt. So, you find out the logarithm. The integral of this will give you the logarithm of n. Applying the limits, you get ln n minus ln n0 is equal to minus lambda t. Then we take exponential on both sides so that you get n is equal to n0 e raised to minus lambda t. This is the famous radioactive law, which will be familiar to all of you. Now from this, the importance of this equation is, from this equation you can find the time of decay of a sample. It is given as small t is equal to 1 by lambda ln n0 by n, can be calculated. Next we come to radiometric dating. Now the radioactivity can be used, the phenomenon of radioactivity can be used to establish the age of biological as well as geological samples. Now for biological samples we use radiocarbon dating, and for geological samples we use geometric dating or geological dating. Now what is the principle in both these cases? The ratio of the amount of radionuclide and the stable daughter in the specimen can be used to determine the age of a sample. Greater the portion of the radionuclide, older the sample. That means that much of decay has taken place. To date biological samples, as I told you, radiocarbon dating is used. Now let us see how that process is done. Now cosmic rays from outer space collide with the atoms in the atmosphere to form secondary particles. Among these particles, there are neutrons which will react with the nitrogen nuclei in the atmosphere to form radiocarbon. Neutrons react with the nitrogen nuclei in the atmosphere to form radiocarbon. This is radioactive carbon. Normal ordinary carbon is C612, whereas radiocarbon is C614. The radiocarbon then undergoes beta decay, and it can decay into nitrogen 714 with a half-life of 5760 years. Now the radiocarbon, although it undergoes decay into nitrogen 14, the cosmic rays coming from the outer space will replenish the amount of carbon 14 in our atmosphere. Now this radiocarbon will combine with oxygen to form carbon dioxide. Now, as you know, the green plants will take in carbon dioxide during photosynthesis, and the animals feeding on these green plants will also take in this carbon along with the when they consume the green plants. Now, when both green plants and animals take in, uh, what will happen is the the radiocarbon will also enter their body together with the ordinary carbon. And during their lifetime, when they are alive, the ratio of radiocarbon to ordinary carbon always remains a constant. But once the plants or animals die, they they no longer take in the radiocarbon, and the radiocarbon amount begins to decay. The radiocarbon decays to nitrogen that we told earlier. Now, depending on the amount of radiocarbon left behind in the sample, the age of the sample can be determined using the equation T is equal to 1 by lambda N0 by N, where N0 is the initial amount of carbon present, radiocarbon present, and N is the amount of radiocarbon present in the sample whose age has to be determined. So, I hope this is clear to you. Next, we come to geological dating. The same method is used, but here the radionuclide used is not carbon 14, but other nuclides like thorium 232, uranium 205, rubidium 87, etc., which has larger half lives. This is because to find out the age of a geological sample like a rock may be about 50 billion years or 4.5 billion years, 50 billion years. It will have a larger lifetime. So, to find the age of such samples, we have to use radionuclides which have larger half-lives. So, the same process is used, but here the sample is different. So you can use rubidium, thorium, uranium, etc. And the stable daughter nuclei formed here is when you use potassium, radioactive potassium, it is argon. Rubidium, it is strontium. See, all of them have very large lifetimes, and they can be used to find out the age of the geological samples. And in this video, last we come to radioactive series, in which the radioactive nuclides found in the nature are members of any of the four above series. So either they belong to the thorium series if they have a mass number like this, 4 into n, neptunium series, mass number in the form 4n plus 1, uranium series mass number in the form 4n plus 2, actinium series for if they have mass number in the form 4n plus 3. And these are their stable end products in all these cases. So all the radioactive nuclides belong to any one of these series. That is, their mass numbers will be in any one of these fashion. So if the mass number is in the form 4n, then it belongs to a thorium series, and its end product after all kind of radioactive disintegration, the stable end product will be lead 82 to 08. If the mass number of a radionuclide is in the form 4n plus 1, then it belongs to a neptunium series, and its stable end product will be bismuth 83 209. If its mass number has the form 4n plus 2, then it belongs to uranium series, and its stable end product will be lead, and so on. So these are the four important radioactive series. Now I hope this video is clear to all of you. If you have any doubts, please do contact. All the things discussed here, I think you have learned in your previous classes. That is why I covered all these topics in just one video. So if you still have any doubts, please do contact. Thank you.